Hi, everyone. We're back with another story for our newest on-demand webinar series, Innovation with Tech During COVID-19. In this series, we explore how our customers and partners have innovated to combat challenges posed by this current pandemic, whether that is through building new apps, forging new partnerships, or using technology in a new way. We're going to do things a bit different this time around and talking about how some of our very own Relativitians used our platform to help with research efforts related to the pandemic. But first, I'm Mike Obregon. I'm an account manager on our developer experience team, and I focused on strategic third-party relationships. Some of you may be wondering, why does this guy look so familiar? And the answer is yes, I am famous. I was one of the hosts of this year's Innovation Awards. Actually, some of the applications and stories we discussed this year at the Innovation Awards are included in this on-demand series, so be sure to check them out. Okay, now on to our programming. Today, I will be chatting with a team who worked together on a CTA put out by the White House and other agencies for the data science community to use artificial intelligence and machine learning tools to help researchers find the answers they needed related to COVID-19. We have Trish Gleason, a product manager, Alex Wilcoxon, a software engineer on our analytics team, and Rebecca Burway, a data scientist here at Relativity. This team worked together to use Relativity to help answer some of the researchers' questions quickly. Hi, guys.
Hello, good morning.
Hello.
So Trish, why don't you set the scene for us here? Can you share what the White House asked of the data science community and how you came across this call to action?
Yeah, absolutely. So my colleague slacked me about the call to action that was put out by the White House in conjunction with a handful of organizations like the Allen Institute, and it was being run through Kaggle. The call to action was an ask to the data science community to use machine learning and AI to clean up and analyze a data set called the CORD data set that was made up of COVID-related medical studies. Public health researchers, they had thousands and thousands of documents to get through to find answers related to the virus. So these were really high priority questions. Things like, how does COVID impact pediatric patients? How long does the virus live on materials like wood and metals? And that data set was messy. There was duplicative information. It was in a lot of languages. And given the urgency of the situation, the researchers didn't have the time to typically sift through all that information. So they asked the data science community, please use machine learning and help us make sense of this data. And right away when I saw this, I knew Relativity was the platform that could help. These are really the problems we solve in e-discovery every day. And we have a lot of really powerful searching and analytics capabilities. So the first thing I did was I reached out to Rebecca and Alex. I knew they'd be just as passionate about the project as I am.
That's awesome. Rebecca, can you tell us about Kaggle and what that platform is?
Sure. So Kaggle is both a platform and a community. As a data scientist, I've been involved with the Kaggle community for some time, even before I joined Relativity. And this platform brings together data scientists as well as aspiring data scientists to learn from one another. Kaggle hosts competitions where data scientists can use technology to solve challenges and to show their work. So it's really very collaborative in nature. And my role in this project was to find key insights for researchers from the CORD dataset, but also to act as our anchor to the data science and Kaggle communities.
Cool. Okay, so we have the CORD dataset. Trish, walk us through those next steps.
Yeah, so now that we have the data set, we have to get the data into Relativity. And obviously we need to do that before Rebecca can run any analytics. I looked at the data set. It was not in a format I was familiar with, so I pinged Alex, who's an engineer on the analytics team. Him and I have worked together for many, many years. See if he could help. He saw it, he knew he could, and I'll kind of let him talk about how he actually got the data into Relativity.
Yeah, so Trish slacked me and sent me a link to the CORD data set. In this data set, the papers are stored as JSON files that have a particular schema, which is in the screenshot on the left there. This schema defines the metadata about the paper and includes the paper's text. But the JSON structure of these files is made up of special characters that we would want to remove and make so we can make the text cleaner for Relativity analytics use. So I wrote a program that read in the papers and parsed them based on this schema. And then the text that was considered relevant, which would be the title, abstract, and body, was combined into a single text file. The program did this for every document in the data set, and then a relativity load file was created that pointed to all of these new text files. We then use that load file with the Relativity desktop client to load the data into Relativity 1 and start using Relativity analytics.
That's great, Alex. One follow-up question to that. From the time you got the data set, the core data set, to the time it was imported into Relativity, but how long did that take?
It probably took a couple hours to write the program, and then a little bit more to iron out some of the issues with it. And then it probably took half an hour to load the data set once we got it into a place where we could, the Relativity desktop client could access it.
Awesome. Pretty cool how you can get this raw data and get into Relativity that fast. Great. Thanks, Alex. Rebecca, what was your approach to looking into the data?
Yeah, so when approaching the data, we really wanted to do so in a way that would benefit the entire data science community involved in this project. And a key way where we could help, although it's not the most glamorous approach to analytics, was just to dedupe the data. To explain the duplication and why that's important. So in eDiscovery, we usually work with email data. And in emails, the duplicate information is things like email signatures or company boilerplate at the bottom of your emails. And failing to dedupe this information can dirty our results and make it hard to accurately analyze or to cluster the data. Now in the core data set, we didn't have emails, but instead we had research papers and journal articles. So here the duplicate information looks like copyright statements. For example, if two research papers were published in the same journal, then they would have the same journal and copyright boilerplate. So for the core data set, we used Relativity's textual near duplicates and repeated content ID to identify over 4,000 duplicate articles, as well as a handful of commonly repeated phrases. And so this helped us to prepare the data so that other Kaggle users could build more robust AI tools on top of it. A separate thing I think would be cool to show is how we used Relativity's conceptual analytics to extract insights and patterns from the document data. For example, the public health researchers wanted to understand comorbidities and risk factors between COVID-19 and other diseases like cancer and chronic respiratory diseases. So I used Relativity's keyword expansion to find concepts that were linked to those diseases. With those concepts, we found many more relevant journal articles that would have been missed had we not used Relativity's machine learning tools. Great, so to show you this workflow, this is an actual list of chronic respiratory diseases that we got from the Kaggle community. So as you can see, it's a really short list of diseases. There are only 4 of them here. And of course, there are more diseases than just these 4 in the core data set. So let's investigate. Let's take emphysema as an example. Let's shift over to Relativity. And here we have already loaded the COVID-19 journal articles, as Alex mentioned, and I've already built a couple of search indexes. Here I have a DT search index. So I'm just going to search for emphysema here. And we get 535 journal articles. So to find diseases related to emphysema as a chronic respiratory disease, let's use this conceptual analytics index that I've already built and its keyword expansion feature. So usually keyword expansion shows up in a pop-up. In order for you to see, I'm just going to copy that URL into a new tab. So this is the keyword expansion, and we're going to put emphysema here to the search index. Okay, so here with keyword expansion, we're seeing other words in this document corpus that are related to emphysema. So as you can see, we see other forms of the word emphysema, as well as words related to breathing and airways. To find other diseases, since I've done this before, I know we'll see some if we search for bronchstar. Okay, so here we start to see some more diseases like bronchiectasis, bronchoconstriction, and bronchomalacia. So let's take bronchiectasis as an example. So now we found using keyword expansion another disease in this data set. So we can go back to that DT search and search for documents that have the word bronchiectasis and not emphysema to see how many documents would we have missed if we didn't know about this disease. And we see we have 431 new journal articles that are about bronchiectasis and not emphysema, right? So you can actually iterate on this pattern, right? So I can take this keyword bronchiectasis and put that back into keyword expansion and find even more diseases. So this is an example of the workflow that we were using.
Wow, that's great, Rebecca. Thank you. A really unique way to showcase the power of the platform. That's great. Thank you for sharing. Rebecca, I'd also love to talk about the experimental nature of AI and how you use relativity to try something new, as we just saw. So can you expand on that and how it applied to the core data set?
Yeah, of course. So one of Kaggle's goals was to build an AI-powered literature review, meaning they wanted to create machine learning that would auto-summarize COVID-19 journal articles so that public health experts could decide quickly whether or not they really needed to read the full article. So I played around with tools in Relativity to see how we could contribute. We decided to focus on journal articles related to the symptoms or asymptoms of pediatric patients. We found these articles using regular expression searches in Relativity. And then we experimented with new AI techniques, such as modern vectorizers and clustering techniques, to automatically extract the ages of those study participants from the journal articles. So on this slide, this is a data visualization of some of those techniques. Here we are trying to separate age-related phrases from phrases that just contain any old number, such as a date or another type of statistic. You can see the age-related phrases represented by orange dots in the middle, while the other numeric phrases are represented by blue dots. And those blue dots have a higher density on the upper right side, while the age-related orange phrases cluster in the middle. So this is an illustration of an intermediate step in the analysis that helped out us to pick out those age-related phrases as a unique cluster. One of the powers of AI is that it can help us be more precise. So currently we're classifying entire documents as relevant or not relevant, but eventually we'll be able to pinpoint segments or sentences in documents that are particularly relevant. This work with the core data set, that was something like an exercise in doing that, in being more precise and pinpointing the ages of the study participants.
Awesome. So Trish, what's the current status of this project?
Yeah, so the Kaggle Challenge did end. We have a team at Relativity that recently met with the Allen Institute, which is one of the organizations that sponsored the challenge, and the medical professionals all around the globe are still using this data set. Also, they're producing a short documentary on the project for a series on the merits, so stay tuned for that in early 2021. For me personally, it was cool to be involved with the project because when COVID hit, I was probably like a lot of people at home reading about it, watching the news, and I wanted to help. I just didn't know how. You know, I'm not a medical professional. I'm not an essential worker. So, you know, when I saw this challenge, I knew it was my chance to get involved, and I knew it was a way for our team to contribute in a small but very meaningful way.
Great. That's an interesting point, Trish. Alex, what made you want to get involved here?
Yeah, so as we've built up analytics functionality in Relativity over the years, I knew once we could get the data into the platform, we could produce results useful for the public health researchers. And I like seeing Relativity analytics being used on data sets that we're not used to using day in and day out in our testing that we do here. And it was cool to get to help out with this project that benefited COVID research.
For sure. Thanks, Alex. Rebecca, being a data scientist, what was your motivation to participate in the Kaggle Challenge?
Yeah, I enjoyed the opportunity to work on a large-scale urgent problem and also to collaborate with data scientists around the world and see what Relativity could bring to the table.
Great. So I'd love to end our conversation here on the potential of AI. It seems like using machine learning tools was key here in helping to solve a growing and global problem. So let's head on this from two angles, and we'll go to you, Rebecca, as the data scientist. But what are the limitations of AI and what's the potential there?
Sure. I think there's great potential in AI, especially for multilingual data sets. You see great strides being made in Google Translate, as well as in the democratization of these tools. Also, opportunities for AI to help with compliance. For example, entity extraction is getting a lot better and could be very useful for identifying PII and being compliant with laws like GDPR. As for limitations, I think you still have to be very careful about how much compute AI takes. Whether you're running these heavy AI calculations on-prem or in the cloud, they still take quite a bit of compute and sometimes even new hardware like GPUs or TPUs. So you have to watch out for those rising computing costs. And in addition to the financial costs of computing, there's also an environmental cost. Computing takes electricity and energy, and we all want to be responsible users of that limited resource. So that said, this is a well-known problem, and researchers are actively working to build more efficient and reusable lower compute solutions. I just think it'll take a little longer.
Trish, Alex, Rebecca, it is always amazing to see how we can extend our platform in innovative ways and how you collaborated to contribute to a very important effort. Thank you so much for joining me today.
Thanks, Mike.
Thanks,
Thank
Mike.
you.